All right, so we are going to find square roots and compare real numbers. Okay, so all positive numbers have a square root. They have two square roots. They have a positive square root and they have a negative square root. But when you type it into your calculator, you are only going to get the positive answer. All your calculator is going to give you is the positive square root, but technically there is a positive and a negative answer. This is called the radical symbol. Square roots are called radicals. So the symbol kind of looks like a divide sign with a little extra tail. Hopefully you've seen this symbol before. And then whatever is underneath is called the radicand with a D. So that's just something to remember, that your calculator is only going to give you the positive answer, but it technically has two. So like the square root of 9 is technically plus or minus 3. So positive 3 and negative 3. Okay, so we're going to evaluate the expression. So square root of 36 is 6, and it's technically, you put this symbol right here, not 7. You put this symbol right here to demonstrate positive 6 and negative 6. Okay, and then square root of 49 is 7, so we're going to do plus or minus 7. Okay, so now negative square root of 4. So we're going to actually make this negative. This would have one answer. So square root of 4 is 2. So our answer here would be negative 2 because the negative's on the outside. And you actually can't take the square root of a negative number. So if this negative was on the inside, we wouldn't be able to solve that. You'll learn how to solve them in Algebra 2, but you don't learn that in Algebra 1. Okay, so we're going to evaluate both of these. I think you have 4 of those on your paper, on that box. So evaluate these 4. Okay, so negative square root of 9, you would get negative 3. Square root of 25, plus or minus 5. Negative square root 81, negative 9. And then plus or minus square root of 64 would be plus or minus 8. Okay, so the next thing you guys have there, it says perfect squares, I believe. So we are going to create a vertical list. I can't fit mine vertically on one slide, but if you guys go down vertical, this is a lot easier to look at than like columns. We're going to create a perfect square list. So perfect squares happen when you have an integer squared. So like 1 times 1 is 1, 2 times 2 is 4. So these are going to be pretty well memorized pretty quickly just by doing problems. So 1 squared is 1, 2 squared is 4. So if you would just write this vertically, and these numbers are what we call perfect squares, and you will see these numbers used and repeated all the time in algebra and geometry. So basically from here on out in math class, you will see this set of numbers repeatedly all the time. Come up in a bunch of different ways, not just having to do with square root. It always has to do with the square root, but not just having to do with like a lesson about square roots. You'll see them in other ways. And this is actually not hard to memorize once you just start doing some problems. Okay, I have up to 15 memorized. I think that's generally the ones that you'll see. I don't have anything past that. really memorized, except, for example, I know that 20 squared is 400, but I don't have all the ones in between 15 and 20 memorized. Okay, so you'll refer to this list a lot until you get it memorized, and then you won't even have to write it down. Okay, the top of a folding table is a square whose area is 945 square inches. Approximate the side lengths of the tabletop to the nearest inch. So here we have our perfect square list extended way beyond what we did. If the square footage of the table is 945, estimate where it's going to lie between. So we're talking about the square root of 945. What two integers is it going to be in between on this chart? 30 and 31. So that's going to be greater than 30, and it's going to be less than 31, right? So it's going to be, if you were to calculate this, it would have to be 30 point something. Now, if we don't use a calculator, what does it lie closest to, 900 or 961? 961, right? So that tells me that it's going to be it's going to be above 30.5, probably very close to 31. So we could, if we really had to estimate this, we could say about 31 inches. If you had to give like a rough estimation and didn't have a calculator, you know it's going to be closer to 31. So I would estimate it about 31. Okay, so we're going to try that again a couple times. So we're going to approximate. Okay, approximate means don't type it into your calculator. Approximate means exactly that, like estimate what it is. So if you look at your perfect square chart, where is 103 in between? 10 and 11, right? So the square root of 100 equals 10, and square root of 103 would be in the middle there. We don't know what that is. And then square root of 121, which equals 11. So I'm just going to write that, my two integers there. Okay, so we know that it lies between 10 and 11. And would it be closer to 10 or 11? Closer to 10, right? 10 point something, probably really close to 10. All right, so let's look at 32. So look where 32 lies in between. So it goes in between 5 and 6, right? Because you have square root of 25 would be less than the square root of 32, would be less than the square root of 36. And those integers would be 5 and 6. Okay, for the negative problems, we're going to just do them like normal, but include a negative number in our integer. So where is 48? Between what?
6 and 7.
Okay, so square root of 36 is less than square root of 48 is less than square root of 49. So this would be greater than, it's kind of tricky though, because think about it, is negative 6 or negative 7 greater? Negative 6 is technically greater, right, than negative 7. So I'm actually going to kind of flip-flop this when I write my negative. And I'm going to write negative 7 is less than negative square root of 48. And that's less than negative 6. Because our negatives number line kind of goes backward from our positive number line. Okay, 350. Our chart went up to 225. So let's maybe extend it a couple. What would be this perfect square of 16?
250.
What?
250.
Okay, so 200, we need to get to 350, right? Yes. So square root, perfect square of 17. 17 squared.
29.
What?
29.
And 18 squared.
3.
324.
Yeah.
And 19 squared. 362.
Yeah.
And I know 20 squared is 400. So 350 is going between 18 and 19. Everybody agree? Okay, so I'm going to go ahead and include my negatives. Which one would I do first because it's negative? 19. So negative 19 is less than negative square root of 350 would be less than negative 18. Okay, on the next one, you have this printed on your paper, but it might be hard to read. I don't think you really need to copy all this down again, but irrational numbers, it's the square root of a whole number that's not a perfect square is an irrational number. So same rules apply to what we did before with the irrational numbers. So if it is a terminating decimal or repeating decimal, it's rational. But if it's irrational, if it's like never repeating or terminating, okay? So here are some examples of irrational square roots. So square root of 2 is not terminating or repeating. That would be an irrational number. And then square root of 14 would be irrational. Okay, so what we're going to look at is we're going to say on the chart, is it a real number? Is it rational or irrational, integer or whole number? So you can use your calculator for this and figure out square root of 24. And see what you get. Should be 4 point something. Keaton,
8, 9, 8,
like a bunch of random numbers.
It's just 8,
8, 9 repeating. Okay, so is that a real number?
9.
Yes. Is that rational? No. Is it irrational? If it's not rational, it's got to be irrational. Those have to be one or the other. Is that an integer? Is an integer a decimal? No. And is it a whole number? No. Okay, square root of 100. That's on your perfect squares. So that is 10. Is that real? Yes. Rational? Yep, 10 is a rational number. Can it be irrational and rational at the same time? No. Integer? Yes. Whole number? Yes. Okay, square root of 81. Negative square root of 81. So that would equal what?
How do we put that into a calculator?
You do a negative on the outside, like the negative sign, and then square root 81. Okay, what would that equal? Negative 9. Is that real? Yes. Rational? Yes. So it would not be irrational. Is negative 9 an integer? Yes. Is it a whole number? Negatives aren't whole numbers. So no. Okay. We're going to look at numbering from least to greatest, I think is your next problem. So order the numbers from least to greatest, and it gives you a mixture of decimals and fractions. If I were to approach this, what would be my best option to get started?
You're making them all the same.
I agree with you. Make them all the same, right? Like all decimals, all fractions, make them all the same. Personally, I'm much better off ordering in decimal least to greatest than I would be a fraction. Unless they were common fractions, like 3/4, ones that I know. So I would convert all of these to decimals, in my opinion. That's what I would do. So 4/3 is a decimal. I do know that without calculating it. Would be what? 1.3 repeating. What's 5 square root of 5? And then put a negative with it. What? Okay. Negative 2.2, and then square root of 13. 3.6. And then I'm going to drop down negative 2.5. And then what's the square root of 9? 3. And then I just have to order these from least to greatest. So that's how I approach it, is I convert them all into the same format, like all decimal or all fraction, whatever I want to do. And then I order them from least to greatest. All right, so the next slide has another, is it rational, irrational, integer, or whole number? I think we're probably okay with not doing this again, if you guys think we are good with that. Okay, so now we're going to look at some of those if-then statements that we did earlier in the chapter. Rewrite the given conditional statement in if-then form, then tell whether the statement is true or false. If it's false, give a counterexample. Remember, a counterexample was like one thing that could prove whatever it was wrong. So given, no fractions are irrational numbers. So that's the information that we're given. We're going to write an if-then statement. Okay, so if a number is a fraction, okay, so this is basically saying if a number is a fraction, then it has to be irrational. Then it is irrational. Okay, so then we need to decide, is that true or false? That's basically saying every number that's a fraction is irrational. Is that true or false? False. What would be an example of a fraction that's rational? Remember, it has to be terminating or repeating. 1/3, 1/2, right? So any of those would be examples of a fraction that is not irrational to prove this wrong. Okay, so we have a few more of these to do. So again, given, all real numbers are rational numbers. So we need to make an if-then statement. So this is our first part. If a number is real, okay, then what? If a number is real, then, and then the second part, then it is rational. And is that true or false? If it's a real number, then it's rational. Look at that chart we already made. Did you have any that are real numbers that weren't rational?
Yeah.
Yes. So that makes this false. And what was an example of a real number that wasn't rational? I think there was one on there. Square root of 24. So there's lots of examples you could put right here. It doesn't have to be the square root of 24, but this is an example of a real number that happens to not be rational. Okay?
What do you mean by real number? I don't know what you're
A real number, okay, that is kind of confusing because you guys really don't know about numbers that aren't real. But in geometry and algebra 2, you'll start learning about a set of numbers that are not real. So the square root of a negative would be an example of a number that's not real. Like I can't do square root of -2 with the negative on the inside of the radical. That would be not a real number. And when you get in algebra 2, you'll learn how to actually solve that, but we don't do that in algebra 1.
Why isn't the square root of 24 real?
It is real.
Then-
Square root of 24 is real.
Oh, it's just not rational.
Yeah. Okay, so again, all square roots of perfect squares are rational numbers. So this is our if part. So how about if a number, we could just say if a number is a perfect square. If a number is a perfect square, okay, then what? Then it is rational. Okay, would that be true or false? Think about all those perfect squares, that chart you wrote down. Are those numbers rational? Yes. So that would be true. Okay, I want you guys to try this one. So create the statement and then you'll say true or false. And if it is false, that means that. Okay, so I put down if a number is a repeating decimal, then it is irrational. Okay, true or false? Peyton?
True.
If it's a repeating decimal, it's irrational?
Oh, wait. No, it's false.
False. And what's an example of a repeating decimal that's rational? 4.15 repeating?
8, 9.
Okay. So really, you could put anything here that's repeating, like you could put 0.3 repeating, anything. All of those would be examples of rational numbers. So for your assignment, you're going to do worksheet 2.7.